So let's say that we have n random variables denoted by x1 through xn. Whenever we have random variables, there is always an experiment in the background, but we typically don't care that much about what this experiment is, since all of the information about the random variables will be summarized in the joint distribution. But it's there. There is a sample space S, and these random variables are just functions from the sample space to the real numbers. x1 is a function from S to R, the same with x2, and so on, the same with xn. So if I have a sample space, the randomness takes place when nature or chance or whatever you want picks one of the outcome in S, which it does according to some probability measure. Then each of these n functions will simply map this outcome into a real number. So x1 maps omega into a real number that we can denote by lowercase x1, and so on, all the way to xn, which maps omega into xn. It turns out to be very convenient to collect these n random variables into a vector. So we'll denote this vector simply by x with no subscript. In print, this is typically denoted using boldface x. So this x will be an n by 1 column vector containing all the random variables, x1 through xn. So a random vector is simply nothing more than a vector of functions. If omega is one of the outcome in the sample space, then capital X of omega is then defined as evaluating each of these functions at omega, xn of omega. So x of omega will simply be x1 through xn, and this is an n by 1 vector of numbers. Capital X is an n by 1 vector of random variables, while x of omega, evaluating x at a particular omega, will give me an n by 1 vector of numbers. This vector is an element of Rn. This allows us to draw a nice picture. I have a sample space S, one particular outcome, and instead of drawing n arrows, one for each random variable, which will be very messy, I can now just draw one arrow, and this is my random vector x, and it will now map this omega into the codomain, which is Rn. So we can write it like this: the random vector x is a function with domain S and codomain Rn. We say that x1 through xn are continuous if there exists a joint PDF f of x1 through xn, such that we can calculate probabilities by integrating this joint PDF. If we denote by x the n by 1 vector containing all these x1 through xn variables, then it's also common to write the PDF simply as f of x, where in script this x would be bold to remind us that it's really a vector containing n variables. Using this notation, we can write probability that x belongs to A is the integral over A f of x dx, where A is an arbitrary subset of Rn. This integral is really now a multiple integral containing n integral signs, and the symbol dx is really dx1 through dxn. The use of vectors will allow us a very compact notation. If I have two random vectors, x being an n by 1 random vector and y being an m by 1, then if they're continuous, I can consider the joint PDF of these two random vectors, which we then simply denote by f of x, y. But in this case, it is actually a function of n plus m variables. It's a function of x1 through xn and of y1 through ym. If I have such a joint PDF, I can find the marginals, and the vector notation will allow me to write the formula for the marginal in a pretty much identical fashion that we're used to from the case when we have two random variables. So the marginal of only the x random vector will be equal to, well, we now need to integrate away the y random vector. So it'll be an integral over all possible values of y, f of x, y, dy. But keep in mind, this single integral notation actually hides m integral signs. And this dy is really dy1 through dym. Similarly, the marginal of y, we simply integrate away x, f of x, y, dx. We define independence between random vectors in the same way as we define independence between random variables. So x and y are two independent random vectors if the joint PDF is equal to the product of the marginals. If we have independence of two random vectors, x and y are independent, then that will imply that every random variable in the x vector will be independent of every random variable in the y vector. Finally, we can define conditional probability density functions. So fy given x, yx is simply defined as the joint PDF divided by the marginal of x. Identical formula to the case when we have two random variables, but the notation hides a little bit of complexity because the right-hand side is now a function of n plus m variables.